Good afternoon, and welcome to today's webinar hosted by the South African Institute of Physics. I am Rudolf Erasmus from the University of the Witwatersrand and SAIP Council member hosting this webinar. Today's presentation will be recorded, and the recording will be made available on the SAIP Facebook page shortly after the conclusion of the presentation. Attendees are requested to pose any questions they may have after the presentation, when I will facilitate the question and answer session. The purpose of these webinars is to communicate on a wide range of topics that are relevant to physicists, and today's presentation is by Professor Marcus Butcher from Northwest University. Professor Butcher obtained his PhD from the University of Bonn, Germany in 1997, having done his PhD research at the Max Planck Institute for Radio Astronomy in Bonn. He was a postdoctoral fellow at Rice University in Houston, Texas, from 1997 to 2002, which included a NASA Chandra postdoctoral fellowship from 1999 to 2002. He became assistant professor at Ohio University in Athens, Ohio in 2002, associate professor in 2007, and full professor in 2012. In 2013, he moved to South Africa to take up the position of Saatchi Chair of Astrophysics and Space Physics at Northwest University in Potchefstroom. His area of expertise is theoretical high-energy astrophysics, with special emphasis on extragalactic sources, such as active galactic nuclei and gamma-ray bursts. It is my pleasure to ask Professor Butcher to present his seminar with the title, Active Galactic Nuclei as Astrophysical Neutrino Sources. Over to you, Marcus.
Thank you very much for the introduction. Yes, so I will give an overview of recent results and developments on neutrino astrophysics, which formed part of the real recent birth of multi-messenger astronomy. Talking about neutrino astronomy, I can really only talk about the IceCube experiment, which has been the only experiment so far to successfully detect a flux of astrophysical very high energy neutrinos. So it is located at the Antarctic Research Station and consists of an array of digital optical modules on 86 strings with 60 modules each that start about 1,450 meters below the surface of the Antarctic ice and covers a volume of 1 cubic kilometer. It detects neutrinos through neutrinos interacting with material and producing secondary particles. These secondary particles produce particle showers that produce Cherenkov radiation. These digital optical modules essentially then image the Cherenkov radiation produced by these particle showers. So before we go on, we should first say that the IceCube detection is not the first detection of astrophysical neutrinos. It's the first time that astrophysical very high energy neutrinos have been produced. It's been known for a long time that, for example, the sun is a source of astrophysical neutrinos, as was the supernova 1987A. But the neutrinos produced in these sources are from nuclear interactions and have typical energies, well, of nuclear levels of order MeV. The neutrinos that we are talking about here are very high energy neutrinos. That means neutrinos typically of energies many million times more. That means 100 TeV to a few peta-electron volt. Detection of these neutrinos through neutrinos interacting with matter and initiating particle showers have essentially three fundamentally different shapes. The ones that are most useful for neutrino astronomy, because they can be nicely traced back to the source of the neutrino, are produced by muon neutrinos. When they interact with matter in the detector, they produce a muon that is deeply penetrating, moves through many kilometers through the ice, and one can nicely trace back where it's coming from to an accuracy of about 0.4 degrees for the highest energies. There are events produced primarily by electron neutrinos, producing an electron in the interaction. The problem is that these interact very efficiently, very rapidly, so they essentially just give one big bubble, a blob of Cherenkov light from all the secondary particles that is very difficult to trace back to where it came from. At best, you can do this to an accuracy of about 8 degrees, so they're not really useful for doing neutrino astronomy in that sense. And then there are very rare events called double bang events, where a tau neutrino interacts with a particle. There's one cascade there from essentially the recoil of the particle that has been interacting. And then when the tau neutrino decays and produces secondary particles, those secondary particles produce a second blob of radiation. Well, it shows the spectrum that IceCube has measured so far. It has been in operation, in full operation with all 86 strings since 2010, so over 10 years now. And what IceCube actually primarily measures the neutrinos are not really the neutrinos that we're interested in as astrophysicists, because there's a huge background that you see here in blue that results from cosmic rays. That means ultra-relativistic particles slamming into the atmosphere and producing secondary particles. Those are really most of the neutrinos that we see. The neutrino spectrum that results essentially reflects the spectrum, the energy spectrum of cosmic rays. That means in this energy range, about a power law with index -2.7. But at high energies, we go above about 100 TeV. IceCube has now measured that there's actually a flattening of the spectrum. So there is an additional component of very high energy neutrinos that are not from interactions in the atmosphere. They really must be of astrophysical origin. Problem, of course, is that, say, if we are around here at 100 TeV, we cannot really tell whether a neutrino that we see is atmospheric or is astrophysical, because essentially both of these source distributions are isotropic. So one can only give at this energy maybe about a 50% probability that a detected neutrino is astrophysical. But the higher the neutrino energy is, the more likely it is that any detected neutrino actually is from an astrophysical source. So now accumulating all these neutrino detections over the past more than 10 years, one could see certain hotspots in the distribution of the sky. Up until very recently, there was, however, never a real significant correlation between any kind of source class and hotspots in the neutrino probability. This has changed now after more than 10 years of data. We now actually have a 3.3 sigma significant correlation of excess neutrino events, excess above atmospheric background. IceCube collaboration has searched for correlations from a list of about 110 potential sources, and this excess correlation is really driven by 4 sources, which are all active galactic nuclei. You see the most significant hotspot actually here, NGC 1068, it's a Seyfert galaxy. All of these 4 sources whose names you see here, I don't need to spell them out, are active galactic nuclei. So from now on, we'll talk specifically about active galactic nuclei and the way they can produce neutrinos and what this neutrino association with AGN might actually tell us about these AGN, as we call them. So AGN, active galactic nuclei, are the nuclei, the central regions of galaxies. This extremely bright, in many cases, the central region outshines the rest of the galaxy by thousands and tens of thousands. They're not steady emitters. They are very variable, in extreme cases down to minute timescale variability, which in itself is mind-boggling that you have something that outshines an entire galaxy by thousands of times, but at the same time, it must be so small that it can be varying on hours or minutes timescales. They are the most numerous sources of high energy, in particular gamma ray emission outside of our own Milky Way. If we look at their optical spectra, quite often they have emission lines. So what that indicates is that there is ionized gas that recombines and gives us emission lines in the optical spectrum. The optical and radio emission is highly polarized, which gives us some indication that most likely here we are dealing with a synchrotron radiation. Relativistic electrons spiraling in a magnetic field produce polarized synchrotron emission. And in many cases, there are relativistic jets outflows, very collimated outflows that are ejected from these central regions. So it is pretty much established now that this phenomenon is powered by a supermassive black hole, typically hundreds of millions or even billions of solar masses heavy, that accretes material from its surroundings, forms an accretion disk that emits ultraviolet and X-ray radiation. This is the source of radiation that ionizes gas in the surroundings, from which we get these emission lines. And along with this accretion goes the ejection quite often of these collimated relativistic jets. Sorry. So now what we actually see in the sky from these jetted AGN depends essentially only on from what direction we are looking at it. If the AGN, the jet system, is oriented in a way that we're looking at it from the side, then often we don't even really see the jets at all. We only see where the jets eventually dissipate their energy there. We form shocks, accelerate electrons that radiate synchrotron radiation primarily that we then see in the radio. So the actual image here of the radio galaxy A is done with a radio telescope. However, there are occasional instances where we are looking almost right down the jet, so that one of the jets is almost pointing right at us. And in that case, as we'll see evidence in a minute, the radiation from that jet that points towards us is very strongly Doppler boosted by relativistic effects. So in many cases, we actually only see that jet that is pointing towards us because that is enhanced due to Doppler boosting, whereas the jet going in the opposite direction is boosted away from us, and so we don't see it. Of course, there is the same kind of jet going in the opposite direction here, but we just don't see it because of these relativistic effects. So these sources where we see the jet almost coming right at us, those are called blazars, consist of subclasses of Bialak objects and quasars, gamma-ray bright, flat spectrum radio quasars. Those are the most rapidly variable of the AGN that we know. Those are the most numerous gamma-ray sources that we have detected outside of our Milky Way. They are dominated in the radio by these radio jets, as you see here, and those are often very highly polarized in the optical and radio. So why do we know that there is this Doppler boosting going on? The strongest evidence there is something we call superluminal motion. If one takes very high resolution radio images with very long baseline interferometry and follows these structures that one can then resolve over many years, the sequence you see here is in real time about 14 years, then one sees individual blobs, individual components moving across the sky. Now, if we know how far away the source is, you can just get the physical distance, the physical velocity that this corresponds to. And what one measures here is that this seems to be moving out with speeds that are 5, 10, 20, in extreme cases up to 40 times the speed of light. Now, luckily, they're not actually moving faster than the speed of light, otherwise we would have to start over with a lot of physics. What is happening is really just a light travel time effect. We have a jet pointed close to our line of sight, so we are sitting as observer here out to the right. And there's something moving along the jet, one of these blobs that we resolve with very long baseline interferometry. But that is moving close to our line of sight, almost with the speed of light. So that means any light that it has just emitted is only just a tiny little bit ahead of it. So all the light that it's emitting over a very long time scale arrives at us actually on a much, much shorter time. One can easily do the math here, from the component emitting light here to the component emitting light here, say some time delta t is passing. But the time difference that we see these two light signals arriving at our observer is then shortened by the large travel time from here to here, which is the projection onto the line of sight over the speed of light. So by this is the time that we actually see any sequences shortened. That means the apparent velocity with which we seem to see things moving across the plane of the sky is then given by this formula. And one can easily check that this gets maximum for a given speed. This becomes maximum if the cosine of the angle, the viewing angle, is equal to beta, the normalized speed over speed of light. And plugging that in means that the maximum that you can get for any real velocity beta is actually the Lorentz factor of this motion times beta. So now, if we know that we have apparent speeds with up to about 40 times the speed of light, that means that these components must be moving with almost the speed of light with Lorentz factors of the order 10, 20, up to 40 in extreme cases. So what does that do? We all have learned some special relativity. It has several effects. Once we have kind of a headlight, searchlight effect, that due to relativistic aberration, all the radiation is bunched up in the forward direction in a small cone of opening angle 1 over the Lorentz factor. And then there's both the intensity of radiation and the frequency, the energy of radiation boosted by multiples of this Doppler factor here. That's 1 over Lorentz factor times 1 minus beta cosine the observing angle. And also any variability that happens intrinsically in the source is actually shortened by one of these Lorentz, the Doppler factors. That means if we see variability on the timescale of an hour, intrinsically in the source, it's actually a factor of delta that's maybe 10, 20 longer. So this relativistic boosting then results in the overall bolometric luminosity actually being boosted up by 4 factors of this Doppler factor. So if the source intrinsically would have a luminosity that it emits, we seem to infer a luminosity that's 4 delta factors higher. So that's like 10, 100,000 times brighter than the source would be if it was stationary and not moving relativistically towards us. This, of course, is the reason why we see them as very bright gamma ray sources, and that's why we can see them also out to very large distances, very large redshifts throughout the universe. So if we now plot the radiation that we see from these sources across the entire electromagnetic spectrum, so we have here a spectrum going from the radio through infrared, optical, ultraviolet, X-rays, and gamma rays. And we plot this in nu f nu, so that the output actually tells us where most of the power per logarithmic frequency interval is coming out. Then we see that there's 2 separate non-thermal bumps, two components, where there's a low frequency component that starts in the radio and goes into optical, ultraviolet, in some cases X-rays. Those are pretty well established to be synchrotron radiation from relativistic electrons. And then there's a high energy component from X-rays to gamma rays, for which there's actually 2 different, fundamentally different ways to produce them potentially in the jet of a blazar. These 2 ways are called leptonic or hadronic models. In leptonic models, we have obviously the low energy components due to synchrotron radiation from relativistic electrons. So there's electrons somewhere along the jet accelerated in some emission region that, as we know, moves out with a Lorentz factor of 10 or 20 or so. It's likely that that might produce shocks or other ways to accelerate particles to relativistic energies. So these relativistic electrons that result then produce synchrotron radiation in the low energy component. And the high energy emission can then produce by these same electrons, Compton upscattering, seed photons, for example, the synchrotron, or external photon fields to high energies up to X-rays and gamma rays. There's an alternative. So in this model, we're not worried about protons at all. Of course, if there are electrons, you would expect everything to be charge neutral. Most likely there are protons in the jet as well, but they do not radiate very efficiently if they are not accelerated up to extremely high energies. So there may be cold or mildly relativistic protons in there, but they don't really contribute to the radiation. But there's also the alternative idea that one can have actually electrons and protons accelerated to ultra-relativistic energies, that they can both contribute to the radiative output. Then we still make low energy radiation with synchrotron radiation, but high energy radiation would then be dominated by protons. Protons can also produce synchrotron radiation, of course, they're also charged particles, but protons can also interact with target photon fields to make, for example, pi zeros that decay into 2 gammas, or they can produce a charged pion that decays then to muons and further on positrons. And whatever radiation comes out here is then typically at so high energies that it can't really escape, because these high energy photons have a lot of low energy photons with which they can interact in the inverse process of electron-positron pair annihilation. That's gamma-gamma pair production. So the radiation doesn't come out. I hope you can still hear me through the thunderstorm here. So that produces secondary electron-positron pairs that radiate more high energy radiation, more pairs, and so on. So it produces electromagnetic cascades down to energies where the region is optically thin to gamma-gamma absorption, and then the radiation comes out. And these processes, if we actually have this kind of models, if this is realized, then in each charged pion decay, there's actually 3 neutrinos produced. So if we are dealing with hadronic models, then neutrinos are produced, or the other way around. If there are actually neutrinos coming from AGN, that means there must be ultra-relativistic protons present that interact with target photon fields to make the neutrinos that IceCube sees. Can you still hear me properly? The thunderstorm with a flat roof is really not a nice thing.
No problem from our side.
Okay, good. But I couldn't really hear anyone of you, I guess. So let's talk about one very particular event that was observed in 2017. The event called IceCube 170922A after the date, so 2017, September 22nd. You see an animation of the actual event in the detector. So it was a muon track, a muon neutrino detector with a nice track that pointed back in a well-defined direction. An energy of about 290 TeV, and at that energy, there's about a 50% probability that it really is astrophysical. But everybody believed that it was astrophysical because it was coming from the direction of one of our AGN, from where we have this access, which wasn't actually known at the time. And this AGN called TXS 0506 plus 056, so that's after a Texas radio source catalog. That is at a redshift of about 0.3. This AGN is also a gamma ray emitter, and it was in a 4-week-long high state in gamma rays. So the source was active. It was emitting a lot of gamma rays. And as we've seen from the models here, of course, if we have these processes going on, there must also be gamma rays produced through the decay of neutral pions, because if we have peak gamma interactions, photon interactions, then both neutral and charged pions are produced. So you would expect naively neutrinos and gamma rays to be associated with each other. So you can see long-term light curves here on the left over almost 10 years that the Fermi Gamma Ray Space Telescope has been observing so far. You can see that towards the end, the time, so 2017, September 2017, the time that the IceCube neutrino was observed, the flux really goes up, the source goes into a high state, whereas the flux stays very quiet throughout most of the mission of the Fermi Gamma Ray Space Telescope. This now zooms in around the time of the IceCube event. You can see the high state in Fermi-Lat, and even with ground-based rank of telescopes that detect gamma rays at over 100 GeV up to TeV gamma ray energies, there was actually then a detection. So it was clear the source was in a very active state at the time. And that made everybody believe, or almost everybody believe, that this really is associated, source really is associated with this neutrino event. The IceCube collaboration then went back into archival data and looked whether there might have been earlier indications of neutrinos coming from that direction. And in fact, they found that over a period of about 4 months, around December 2014, there was actually excess emission of neutrinos at somewhat lower energy. So one can't really identify any individual neutrino as being an astrophysical neutrino, but there was a statistically significant excess of neutrinos over the atmospheric neutrino background of about 13 neutrinos that must have come from this source. So with that, modeling that excess over the atmospheric background, one can actually determine a flux and one can determine a spectrum. Of course, in most other events where there were individual neutrinos identified as astrophysical neutrinos, if you have just one neutrino, you cannot really tell what the flux is. But with 13 neutrinos over a period of 4 months, you can actually say something. But the big surprise was, if we look back at the light curves that we just saw, this is about the period of this neutrino flare, there was actually nothing happening in gamma rays. So when we had said before, gamma rays and neutrinos must be co-produced in these p-gamma interactions. So why is there no gamma ray activity at the time that we see this neutrino flare? Let's talk a little bit more about the physics of neutrino production. We have already mentioned that in AGN jets, this can happen primarily by protons interacting with target photons, producing pi zeros or charged pions. And the pions then decay into ultimately electrons or positrons and neutrinos. Looking at energetics, one can figure out that about the same total energy goes into photons from pi zero decay as they go into neutrinos. That's typically about 20% each of the initial proton energy. This is plotted here as a function of a target photon field. So we have a photon field that is given by a power law spectrum in energy. And this is just for different spectral indices. You can see the statement that neutrinos and photons take up about the same amount of energy holds, irrespective of what the target photon field actually is. So at what energies is that typically happening? So what energies of protons and target photons do we need to make neutrinos of energies where IceCube sees them over 100 TeV? That, of course, depends on the cross-section. And as many of you might have seen before, the interaction cross-section for photons interacting with protons, this is now here plotted in the proton rest frame, has a very strong peak at a resonance that we call the delta resonance, that then decays to produce pions. To make this even stronger, there are, of course, possibilities to have interactions at higher energies for any given proton. If you have higher energy photons, you can produce through different channels, including multi-pion production and so on. But where are we? Sorry. Where are we here? Sorry. My PowerPoint just went to the wrong slide. I think it went to the end. Let me pick up here again. So if we now essentially average this cross-section over the power law spectrum of target photons for different indices of, is it here, of 1, 2, 3, then you can see as a function of center of momentum energy here now, the interaction probability, that means the number of interactions that happen as a function of the energy. You can really see that almost all the interactions, this is logarithmic scale here, almost all the interactions happen right around here, right at this delta resonance. So for energetics considerations, you can really just focus on what's needed to make neutrinos at delta resonance. One can easily calculate what the threshold energy is. So if we have target photons of order an electron volt, so that optical photons, then protons need an energy of, say, 10 to the 17 electron volt to reach the threshold, at least to enable kinematically this P gamma interaction. And at slightly higher energies, we are reaching the delta resonance. So that relates then to the delta resonance in center of momentum rest frame. Calculate that from the proton energy and the target photon energy. Gives you essentially a relation between the target photon energy and the proton energy that relates to the delta resonance energy squared. Then we know that each neutrino takes about 5% of the proton's energy. Then we can easily see, to produce a neutrino, say, of 100 TeV, the proton then has to have 20 times that energy. But neutrinos undergo the same kind of Doppler boosting as we see from photons. So if a neutrino is observed at 100 TeV, then it's actually produced in the source that moves relativistically towards us with a Doppler factor less. So if the Doppler factor is 10, then it's actually produced only at 10 TeV. And then the proton needs an energy of about 200 TeV. And then to satisfy this condition for the delta resonance, we can easily figure out that the target photons must have energies in the keV, that means in the X-ray range. Now, let's get back to this correlation between neutrinos and photons and why or why not might we expect them. So if we have a dense target photon field with which protons can interact, and the likelihood, the efficiency for a proton to actually do ion production is just given by, well, the length through which the proton travels, staying either in the region or losing much of its energy, times the interaction cross-section, times the target photon density. And the cross-section is given here. But if there are gamma rays produced now, they can also interact with that same target photon field through gamma-gamma pair production, gamma-gamma absorption pair production. That likelihood is then given by essentially the same expression, only there's photons travel in a straight line, so it's really just the size of the emission region times the gamma-gamma cross-section. And if you look at this gamma-gamma cross-section, so that shouldn't be -2, that's centimeter squared. So that's about, well, 1.5 times 10 to the minus 25 centimeters squared. Whereas the cross-section here peaks at some microband and 10 to the minus 30 centimeters squared. So this is 10 to the minus 26 to the minus 27 or so. So that's about 300 times smaller cross-section for P gamma interactions than there is for gamma-gamma interactions. So that means the opacity for photons, the likelihood to be absorbed, is about 300 times larger than the efficiency for protons to make neutrinos. So that means if we actually have a reasonable chance for protons to make our neutrinos, then most likely this emission region is optically thick. That means any gamma rays that come out, that are produced, would not come out, but only they produce electron-positron pairs and produce cascades. Specifically, so where this cross-section then peaks, if we're thinking about, if we figure out what the target photon characteristic energy is, we can calculate what gamma rays then primarily would interact through gamma-gamma absorption with these target photons. That then gives you a relation that it's about 3 times 10 to the minus 5 times the neutrino energy. That means it's exactly these GeV to TeV gamma rays that we see with Fermi-Lat and Cherenkov telescopes on the ground that, yeah, we actually don't expect to see, because most likely this emission region is optically thick. And this might in fact explain why TXS 0506 during the neutrino flare was not showing anything particular in gamma rays. So there's the point again, efficient neutrino production sites are likely to be optically thick to gamma rays, and thereby you don't necessarily expect gamma ray activity to be correlated with neutrino activity. Let's maybe look specifically at some attempts to measure the spectral energy distribution and the neutrino emission from this one source around the neutrino event of 2017. So there have been several attempts. Most of the time when people do hadronic models with neutrino production, they consider, well, that there are relativistic protons that might make proton synchrotron and pion induced processes, and the target photons are often assumed to be synchrotron photons produced in the same region by electrons. But if we do that, remember we said we actually need X-rays in the co-moving frame to make 100 TeV neutrinos. If we have much lower energy target photons, then remember proton times photon energy gave us the delta energy squared for interactions at the delta resonance. So lower energy target photons means you need higher energy protons, and that results in higher energy neutrinos. So the problem with this kind of models is that you produce neutrinos that are actually at way higher energy than the IceCube detected neutrinos. Now also model attempts to model this gamma ray emission that was seen here, really with cascades from pi0 decay and the radiation from secondary particles that resulted from pion production. But the problem with that is the cascades that are produced have a low energy spectrum that is just relatively flat, and those way overshoot any X-ray emission that has been seen from the source. So this kind of models also kind of fail to reproduce both the radiation and the neutrino emission. So the only way to really overcome this is that one says, well, the low frequency optical, radio, X-ray, and gamma ray emission is all produced only by electrons, maybe not even in the same region, maybe somewhere completely different part of the jet. And then you have an additional proton component that makes you the neutrinos, but does not significantly contribute actually to the electromagnetic radiation. This is really the only way that people have been successful in modeling both the radiation and the neutrino emission. So let's maybe, as one last point, consider where could these target photons now actually come from, the target photons that we would need for protons to interact, to make neutrinos, and not overshoot what we see here in X-rays. If the X-rays are actually the most critical band here, if we have too much of these proton-induced radiation processes, they are very likely to overshoot the X-ray emission. So we need protons, again, with about 200 TeV and higher if you produce higher energy neutrinos in the frame of the emission region, and target photons of AeV energies. And we consider a target photon field that is, say, like the electron synchrotron radiation field co-moving with the emission region, then this photon field we would also see directly. It would be strongly Doppler boosted towards us. Remember these 4 Doppler factors, so factor 10,000, 100,000 times brighter than it would be if it was stationary, and it's boosted to higher energies. We would see it at then 16 keV and hard X-rays. And in order not to overshoot the X-ray emission that is seen from the source, so we must limit the energy density of this target photon field that is moving along with the jet. But if we have relatively few target photons to interact with, we need a lot of protons to make a given neutrino flux. And if one figures out the numbers, then the power that you would need in these relativistic protons is just many orders of magnitude higher than anything that the central supermassive black hole of the system can plausibly power. So one can actually rule out that this is a target photon field that moves along with the emission region. But things are much more relaxed if it's a target photon field that's stationary in the AGN and the jet just moves through that, then that photon field is not boosted for us as observers because it's just stationary, but it's boosted into the emission region frame. So that actually helps us in 2 ways. then we would see it, well, at even lower energies, say in soft X-rays or far ultraviolet. And if one figures out all the constraints of the power needed, it can actually all be quite plausible. So most likely we are dealing with target photons here that are stationary in the AGN frame and that we would see somewhere in the ultraviolet or soft X-rays. So what could that be? There have been at least three interesting possibilities of where these target photons could come from. One was suggested actually by Photo-Pion that in fact we have these clouds here that are irradiated by the central accretion disk that produce us the emission lines that we see in the spectra of many quasars in particular. TXS 0506 was actually classified as a BLAC object that does not show very strong emission lines, but in a detailed study, Photo-Pion has actually shown that there are emission lines hidden below a very bright synchrotron continuum. So there is a target photon field, at least at UV energies, that could serve as targets for ion production. There have also been suggestions that these jets are most likely not just one stream and nothing on the side. Most likely there's some kind of radial structure, so there's slower moving material further out and just a fast spine that really moves with these high Lorentz factors in the middle. And then there can be interactions between the two that energize particles even in the sheath outside. That can produce synchrotron radiation at relatively high energies, possibly UV and X-rays, that could serve as targets. Or it can also be associated with more extended regions of the accretion flow itself, when accretion is happening at relatively low rates, and then the accretion disk often heats up and puffs up a little bit and produces kind of a funnel geometry from which radiation could enter the jet. So obviously, nobody knows what really is the source of these target photons, but overall, it is quite plausible that there is a suitable target photon field with which protons in the jet can interact to make the neutrinos that IceCube has identified. That brings me to my summary. So I've motivated that jetted AGN, in particular blazars, are likely and plausible sources of very high energy neutrinos as detected by IceCube. For that, we need about peta-electron volt protons in the jet co-moving with the emission region. We need target photons of co-moving UV X-ray energies. From that opacity constraint, one can say that one doesn't necessarily expect a correlation between gamma ray activity and neutrino activity, even though gamma rays and neutrinos are co-produced in these processes. And at least from the specific case of TXS 0506 plus 056, one strongly favors both the synchrotron and the gamma ray emission being done very strongly dominated by electrons. And the target photon field that we need to make neutrinos with protons is most plausibly from outside the jet, something that we would see as UV and soft X-rays. Thank you.
Thank you very much. There is an opportunity to ask questions. You can either type a question in the question and answer box or in the chat box, or raise your hand, and we can unmute you should you wish to voice a question. I know it usually takes a minute or so for people to type things in. Okay, there is
Anton has raised his hand. Yeah?
Okay.
Can you hear me?
Yes.
Please go ahead, Anton.
Marcus, thanks for a very nice talk. Actually, I really enjoyed it. I have a question. So how to actually produce neutrino flares in BLAC objects, since they don't really have external photon fields?
Well, in BLAC, maybe we can come back to this one here. Even so first of all, for TXS 0506, emission lines have in fact been identified, even though they are not very strong. but there's a very bright synchrotron continuum that outshines them most of the time. That's why it was identified as a BR-like object originally, but most likely there are actually broadline region photons there. But also the other two possibilities are still possible in BR-like objects, right? So the spine sheath geometry, you're very likely to have both in quasars and in BR-like objects. And BR-like objects typically characterized by lower, or at least plausibly by lower accretion rates, are likely to have these radiatively inefficient accretion flows that heat up and produce soft X-rays, in fact, through extended corona. So there are several probabilities that you have target photons.
Okay, thank you.
This Andrew Chen also has a question. Andrew, you're welcome to go ahead.
Yes. So my question is, there have only been a sort of handful of AGN that are sort of hotspots in IceCube. Is there any sign that there's anything different about those AGN compared to like the other, I guess, 107 objects on the list with regard to these models? Like, does that provide any kind of clue, or could it just be sort of pure chance that those are the ones that poke up above the significance? I ask in particular because NGC 1068 is sort of not a typical gamma ray emitting AGN, right? And maybe that's sort of a clue, like the fact that it's a Seyfert galaxy, the fact that there's much more circumnuclear material, and maybe that actually has a higher chance of neutrino production than your typical blazar. I want to know what you think about that.
That is an excellent question, and there hasn't really been a convincing answer that I am aware of. So it seems to be really just a coincidence. And yes, as you say, NGC 1068 shows signs of jet activity, but it is classified as a Seyfert galaxy that are typically not jet dominated. But maybe it gives us an insight that whatever happens is probably very close to the central engine, as opposed to blazars where things might happen still on parsec scales. But there hasn't really been any convincing answer. There doesn't seem to be anything particular that these four sources really have in common that other blazars don't have. Not that I'm aware of. I mean, with individual neutrino associations, of course, the answer is relatively easy if one calculates the probability to see even one neutrino. So if one calculates the expected neutrino flux at very high energies where you identify individual neutrinos, typically for models, you see even for the kind of brightest neutrino sources that you expect over the 10-year lifetime, you expect maybe 0.1, 0.2 so neutrinos. That means if you have 10 of these sources, you detect one. It doesn't mean that one is special in any way. It's just the low probability to even detect one neutrino.
Right. Thank you.
Thank you. All right, there's a question that's been typed in the question and answer box. It asks, would we expect the same relationship between neutrinos and gamma rays for sources in a quiescent state, assuming that the blazar produces neutrinos during its quiescent state?
That would certainly apply to any source and to any state, right? Only that in a quiescent state, most likely the emission comes from somewhat more extended regions along the jet rather than a small localized region. In that case, it's probably easier to avoid this opacity constraint, one would think. But then again, if it's in a quiescent state, then, well, there isn't really any activity that you could associate with a neutrino flare in a sense, right?
Good. Thank you for the answer. Right. Let's see. I don't see anything else popping up right away. Just make sure on the list of participants. I think that seems to be all the questions that that are going to be asked right at the moment. So it remains for me to say thanks again to Prof. Butcher for an excellent presentation. It's very much enjoyed. Thank you for the trouble you went to prepare it and to deliver it. Thank you very much to all the attendees for making the time to attend the webinar. And then thank you also to the SAIP office, who did much of the organization in the background. And without them, we would not be able to do this, these webinars. So thank you again. Have a good Friday afternoon, and I wish you an enjoyable weekend. Goodbye.